The idea of the area under the curve as the integral from 2 points from point A to point B. And you saw that today in your example here when you went through all the candy stuff. What we're going to do today now, though, is actually go through the math behind it. And it's a lot more complicated than you would think. Because, yeah, I know today we just had a bunch of rectangles and we added them up, right? But what happens if I tell you, okay, make 10 rectangles? Or if I tell you, make 6 rectangles? Or make 20 rectangles? Based on the number of rectangles, it's going to keep changing your width. And each of those rectangles is going to have a different height. So we have to constantly be thinking about, back to our functions, the width of something has to do with the x-coordinate. The height of the function has to do with the y-coordinate. So we're constantly thinking about this as we go through this process. So today what we're really going to do is learn 3 different techniques, 3 different ways to do it. And I showed you already last week where it was the left, the right, and then there was the midpoint. But we're going to go into more detail today about how that works. Let's start with an example. Let's say we are looking from... We're looking at the function, so example 1 for today. We're looking at the simple function x squared plus 1. Okay, and we're looking on the interval from 0 to 2. So again, from A to B, from 0 to 2. So the question here becomes, can we figure out the area under this curve from 0 to 2? So the first thing we have to think to ourselves is, okay, from 0 to 2 means I'm only going to be in this quadrant. I know that already, which is wonderful to know. At this point in time, I want to think about what the sketch will look like for this. What is the sketch for a parabola going to look like?
A U? What?
She said to you that he said to you that you said to you, but you was lying, so I do it back.
Like a follower?
So what do we got here?
A U? A U shifted up.
Good. A parabola that does what? It's shifted up. So,
It's on the y-axis.
I already know that yes, the shape will look like this. Okay, that's going to be my general shape there. Everybody see that?
Yep.
But do I care about the blue part?
No.
How come I don't care about the blue part?
In your range.
Not range. Interval or domain. That's the part we're looking at. Okay? Again, we're going from 0 to 2.
You know what I mean, though.
So if we're going, thank you. Appreciate that answer. From 0 to 2. From 0 to 2 is my domain. Again, it's a restricted domain. That's the key here. You're not talking about range. Yes, your range will be restricted. Will be restricted as a result of this. Sure, but we are only concerned about this. So what we're trying to figure out is what is the area underneath this curve. And whenever I say underneath, I really mean between the curve and the x-axis. So as we did today, you saw this. If you had a graph where it was below the axis and then above, this was the first area you wanted, and then this was like the second area you wanted. So whenever you hear this, even on the test, area under the curve, if the curve is negative, then it's really area above the curve in a sense. Okay, but again, you're always looking at the area between the function, wherever it may be, right there, the function itself, and the x-axis. Okay? So that's the example from before that we did today. Now, for this one, there are several ways to do this. There's a left approximation, a right approximation, a midpoint approximation. Now, it also depends on how many rectangles I use. So, let's start with a simple way to look at this. So here, you can leave it on there. I'm just going to go through rectangles now. For this example, again, we're going from 0 to 2. From 0 to 2 here. Now, if I wanted 4 rectangles, that's pretty easy to do, right? Cut something in fourths. You cut a line down the middle and then cut those in between. So 4 rectangles, you don't have to write this, but it would look something like that, really. Okay, fourths. Okay, somewhat like that, yeah. Now, if I wanted to have 8 rectangles, I have to cut it into 8 spots, right? Now, the number of rectangles, what does that dictate to me? The n value, very good. So n is the number of rectangles, so whatever that may be, very good. Now, what does that, as a result of the number of rectangles, what changes?
The accuracy.
Sure, accuracy definitely changes, absolutely. But mathematically speaking, what part of the rectangle changes based on the number of...
The width?
The width. The width. Let's take a look. If you had 4 rectangles, each width would just be 0.5, because this is 1 here in the middle, isn't it? So it's like 0.5, 0.5, 0.5, and 0.5, giving you a total of 2 as a width. But if I had 8 rectangles, now every rectangle is 0.25, 0.25, 0.25, 0.25, 25, 25, 25, 25.
But nothing is still equal to.
Okay? In the end, it's still a full length of 2, absolutely. But each of these rectangles now have a width of 0.25. So the number of rectangles dictates the width of each rectangle also. The more rectangles you have, the skinnier each one is. So if you want to write this down in your notes, as the number of rectangle goes up, the width goes down always. That's a common thing you got to remember. And you'll see this mathematically. You'll see it mathematically. Again, if I have, instead of 8, if I have 16 rectangles, that's what it looks like now. And now all those widths, it's exactly 16. And now, because I cut it in half, it's powers of 2. Now each of these rectangles has a width of 0.125. So the widths keep going down as the number of rectangles goes up. So as the number of rectangles goes up, the widths all go down. That's something that you should just know. Now, if I actually want to go ahead and approximate this, like the real way we're going to do this in class, let's go ahead and take a look. Not even the equation yet, but the method of rectangles. We haven't actually gone into it yet. We've just kind of been arbitrarily picking rectangles. I'm going to label the 1, okay, even though it wasn't on the original graph, just so I know where the midpoint is there. And again, knowing that my graph kind of stops there, so I'm thinking from A to B, again, where A is 0 and where B is 2. Okay? If I want to think about this, I can think about it 3 ways again. Left, right, midpoint. What does that mean? What do the three different things mean to you?
It's where the rectangles line up.
It's where they line up, so what does that mean then?
Yeah, when you're touching the curve.
Okay, but which part of the rectangle? What are you talking about?
Like the center, meaning the...
Do you want to come up and show then?
Sure.
Okay, if I had 4 rectangles here, 4, okay, and I wanted to have a left approximation, what would that look like? 4 rectangles, 4 rectangles left. Do you know?
Left probably, yeah. No. I mean, isn't that just mean like corners, like left corner of the rectangle
Touches the
curve?
Touches the curve. Very good. So when you hear this, you're going to hear it today. You're going to hear L-R-A-M, you're going to hear R-R-A-M, and then M-R-A-M. This means left rectangle approximation method, right rectangle approximation method, midpoint rectangle approximation method. You're going to see this terminology in your book tonight when you read also, RAM. It means rectangle approximated method. Okay? So you're approximating. That's why it's called RAM, rectangle approximation method. Depending on where you start, you're going to either be LRAM, RRAM, or MRAM. And let me show you the example here. If I were to take a look at the first rectangle, and I wanted to start and look at my rectangle, and I know I'm going to have, let's say n turns out to be 4, like I said here.
Okay.
If n is 4, what is the width of each rectangle going to be?
0.5.
How come, Kenny?
Because you divided 2 by 4.
Very good. The whole domain goes from 0 to 2, which is an interval length of 2. If you have 4 of them, you take the 2, which is the interval length, divided by however many there are, and this will give you the width, which is 0.5. So if you want to write this down, if you want to write a little note to yourself, the width is always equal to the interval over the number of rectangles, which mathematically can be written as b minus a all over n.
Can we just say n? Oh.
Okay, b minus a, the end, minus the beginning, 2 minus 0 is 2, divided by 4.
It says b minus a?
Okay, b minus a over n. This is something that you're going to use over and over again, so it's good to memorize that one. And it'll become more apparent. Again, the full length is 2, which is this 2 minus 0. So in our case, we have 2 minus 0 really. Sorry, I didn't put that in there. But it's 2 minus 0 because it's b minus a. But the 0 doesn't matter. Okay, divided by however many there are. So in this case, I can already go like this. Put tick marks every 0.5 now to indicate that's where your rectangles will begin and end. Because again, I'm going to have 4 rectangles. This is the width of my first one right here. This is the width of my second, my third, and my fourth rectangle. All of these have the same width though. Do you notice that? And that's the key here. If they were all different widths, then it becomes a lot more complicated. You have to do a lot more math by hand. When they're all the same width, we're going to see later we can factor something out of the equation. It makes it a lot easier. Now,
So why didn't you just make a like full, what you call it? Full rectangles? Why'd you only put
well, I'm going to do that now. That's what we're going to show how to do this. Now I want to go step by step on how to do this. Here's how you do it. When it's a left approximation, start at the left side of any of the rectangles. So either you start here, when you're looking at this rectangle, you're going to start here. If you're looking at this rectangle that's about to go up, you're going to start here on the left side. If you're looking at the third rectangle, you start on its left side. If you're looking at the fourth rectangle, start on its left side. So you're never going to start on the right sides. Now, if you start on the left side and go up until you hit the function, and then go over from there and drop down. Again, you go up here until you hit the function, go over, and then drop down. Go up until you hit the function, go over, drop down. Go up until you hit the function, go over, and drop down. That would be a left RAM. Again, starting on the left, you go up, over, down. Up, hit the function, over, down. Up, over, down, up, over, down. And what you're noticing here is because this function is an increasing function, and it happens to be concave up, you're going to notice that you're going to have some missing pieces here. Okay, you're going to have missing pieces. Depending upon the first derivative and the second derivative, actually, the increasing, decreasing this, or the concave up, concave down, your approximation will be an undershoot or an overshoot. It's not based on whether it's left or right always. It depends on what the function actually looks like here. Okay?
The middle's more accurate because it balances.
Exactly. Middle is balancing out those errors. That's what we're going to talk about at the end here. So this would be a left approximation. Now, the hard part is this. How do I know these areas without just estimating? That's what it comes down to, right? So, what is the width of all the rectangles again? 0.5. So I know when I do my math in a minute, and I want to find the area of rectangle 1, it's 0.5 times whatever the height is. The area of rectangle 2 is 0.5 times whatever the height is. Rectangle 3 and rectangle 4 are the same thing. 0.5 times whatever the height is. But all these heights are different, and you can see that in the diagram. Again, take a look at the diagram up here. Every diagram has a different height. Now, we might not know what the height is by looking at this alone, so this is where we start to calculate values. What did I say a minute ago? The width represented x. What represents the height? The y value. The y value. So, Kerry, if I want to find the height of the first rectangle, I went up to here, didn't I? And then I went over?
Is that 1?
So I want to figure out to myself, okay, if I know that the function is at x equals 0, I can figure out what the height is and then go over. Well, what's the height here, Carol? It's just 1. Because again, if you plug in a 0, take a 0, plug it in there. What do you get? You just get a 1. So this height here would be a 1. So in this case, the height would be 1. But what about the second rectangle? What's the height going to be there? How come, Carrie? Be careful. You're doing the third rectangle right now, whether you know it or not. What's the value of x here? Isn't this really 0.5? Isn't that really 1.5? So for the second rectangle, when you want to find the height of it, you need to plug in a 0.5 into the original function. Again, when you're using left approximation, you're always going to plug in all of the left numbers in. So for example here, you're plugging in a 0 into this function to give you the 1. Then you plug in the 0.5 up here to give you this height. Then you plug in the 1 to give you the next height. Then you plug in the 1.5 to give you the next height. So here, what you're thinking of is this. This value, stop kidding, this value is really f of 0. This value that you get here, I just mean stop talking please. This value here is f of 0.5. This value here you're going to get is f of 1. And this value is f of 1.5. Again, all we're doing is we're plugging in the heights. So this height right here, I want to figure out what it is. So I know the x value is 0.5, so I have to go up and figure out the height. So go back into the original. 0.5 squared is 0.25. 0.25 and 1, 1.25. Now, the next one, I want to plug in 1 into the function. Because again, here's my left part of this rectangle. This was my left part of the second rectangle. This was my left part of the first rectangle. Because we're doing LRAM, we're using the left side. So the left rectangle is 1. So when I plug in a 1 into my original function, what do I get? 2. Again, 1 squared is 1. 1 plus 1 is 2. So the height of the third rectangle is 2. Finally, the fourth rectangle, its left point is right here. There's the left point at 1.5. I go up. I want to find out that height. So I have to plug in 1.5. What's 1.5 squared? You should know that one. 2.25. Very good. Adding on the 1, 3.25. 1.5 squared comes up so often that it's one that you really should memorize, okay? Again, 1.5 squared is 2.25. That's a good number to have memorized. It comes up over and over. You know how I remember it? Very good, Joss. Very good. 15 squared is 225, right?
Yeah, I just
1.5 squared is 2.25. Move 2 decimal spots because you're squaring. Okay? Again, so my widths are consistent, aren't they? But my heights are what change based on what rectangle I'm looking at. So this height was a height of 1 on the left side. This height was a height of 1.25. This was a height of 2, and this was a height of 3.25. Again, I'm always looking at the height on the left side. So whenever I plug in a number into my function to find the height, it's always the left side. This left side is 0. That goes there. This left side is 0.5. This left side is 1. This left side is 1.5. Now, you could sit here and add them all up. That's fine. But notice, what's in everything? The 0.5. So area total is really the sum of all the areas. Right? The total area is the sum of the 4 areas. So in our case, I can write it out because it's very simple. I might not always write that out because there might be like 10 rectangles. Okay? But again, notice for every single one of these, the total area, you're going to have a 0.5 in everything. I'm going to use an asterisk for times right now, just to show this difference here, because I know it can be a little confusing. Okay? Again, the first rectangle had a height of 1. The second rectangle had a height of 1.25. The third had a height of 2. The fourth had a height of 3.25. 0.5 is in everything. So you could simply multiply through and add everything up. I would just factor out the 0.5 though. Again, I would just say this. Again, just like variables, if you have an x in every term, you can factor it out. There's a 0.5 here, 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 and here, so you factor out the 0.5. Add up the numbers in here. 2.25 and 3.25 is 5.25 and 2. Very good. And half of 7.5. What is it, Karen? Very good. So that is my approximation using the left-hand technique. Now I'm going to jump right to the right-hand technique for the same problem. Okay, the exact same problem. I'll give you another second to write. You're still writing. The same problem, but we're going to use the right technique. Christian, what do you think is going to happen with the right technique?
We're going to start from the right side.
Good. And what do you notice about the answer? Will it be bigger or smaller?
Bigger.
Because that's an overestimate, and this was an underestimate. Again, notice we're missing all those spaces here. Remember all these little spaces? That makes it an underestimate. The right-hand approximation will be an overestimate. Okay?
When we're doing these problems, will they tell us if they want the L?
Yes, absolutely. Absolutely.
So we have to.
On the problem, a lot of these kinds of problems are multiple choice. They will give you this. They'll tell you the number of rectangles and which type of approximation to use. Again, number of rectangles and the type of approximation. Okay.
In the test, they would ask us to like manually do either left, right, or like on the part 2.
Yes. It would be multiple choice. This would not be a part 2. It's rare. Sometimes you know what they'll do? They'll give this to you as a part 2 and say approximate, and then they'll say find the exact answer using integrals, which we haven't done yet. So if it's a part 2, that's the only reason it would be a part 2. It would be an approximation for like part A, and then they'll have B and C still. Okay, it'd be the very beginning part worth like 1 or 2
So
points.
if we want the exact, can we just do the middle one?
If you want the middle is a better approximation though. It's not exact.
Oh.
It's never exact. Exact is actually using the limit, which we haven't even gotten to that yet. Okay. All right. Same function. Same right, guys. Everything else the same except now it's right hand. So again, if I'm using the same amount of rectangles, I'm going from 0 to 2 still, and I'm still looking at the function x squared plus 1, and I want to know R, A, M. That's a terrible handwriting. Let me just redo that. R, A, M. Okay, Okay, RRAM. So, in this one, I have 4 rectangles still. 1, 2, 3, 4. How do I have 4 rectangles? Because n was equal to 4. Each of the widths is still what? 0.5. It hasn't changed. Now, instead of starting on the left and going up, I have to start on the right. So start all the way over here. Go all the way up until you hit the function. Go over, come down. Same thing, the next one. Go all the way up. I'll use another color. Go all the way up until you hit the function. Go over, come down. Go all the way up until you hit the function. Go over, come down. And finally, go all the way up until you hit the function. Go over, and come down. And notice, all of these are overages. And that's the idea of the midpoint. That's where that came from. So in this case now, take a look at the difference here. If I want the height of this rectangle, I have to use the right side for the height. If I want the height of this rectangle, I have to use the right side. I have to use the right side. I have to use the right side. So remember last time how we kept plugging in the left sides into the function? And if you look back at it, just so you're clear, last time we plugged in f of 0 for the left height, f of 0.5 for the left height, f of 1 for the left height, f of 1.5 for the left height. Now we're going to use all the right heights, these 4. So instead of using 0 to start, we're going to start by using a 2, and then we're going to use these 3 again. Okay, so you're going to notice there's some overlapping. Only one thing actually changes, which is your endpoints. It's the only thing that changes here. So let's go ahead and do that. If I want the height of this function here, I want to know what is the height of this first rectangle. So I have to figure out what is f of 2, pretty much. Okay? Again, I'm trying to figure out what is the height of the function. The height of the function means f, well, at what location? At x equals 2, right here. So you simply plug in a 2 and you get 5. So the area for this one, okay, is going to be, you're going to have a 0.5. So let's write these out. I'm going to write them in this order. I know it sounds weird. I'm going to write them like this now. I'm going to start with the 4th one on the right, okay? So it's 0.5 as a width, and the height would be 5 in this case. Again, the width is still a half. This width is 0.5. This height is 5 up here. Next one. What is this width here? This width is still 0.5. Now, if I start here, and I go up, I realize, okay, this is the location that will indicate the height. So what is the x value here?
1.5.
So this height is really represented by f of 1.5. So if I plug in 1.5, oh, I did that last time, didn't I already? And I got 3.25. I did that in the last example. So this one's going to be 0.5 times 3.25. Then I need to know what this height is. Well, this width is still 0.5. Now I have to figure out what is the height up to this point. How do I know the height at this point? I have to know the function's value at x equals 1. So I'm really looking at f of 1 now. But I did f of 1 already. I did f of 1 in the last example. It turned out to be 2. So this is an example where your table function, your calculator, is going to be used a lot. Okay, you're going to use that table function over and over. Finally, the last one here, I want to plug in a 0.5 to get the height here. Again, to get that height, I need to plug in 0.5. What do I get? 1.25. What is the total area going to be? Not numerically, but tell me, how do you do it?
You factor out the 0.5.
Very good. Sum of all the areas. So in this case, look at this one, and then look at the last one. What you'll notice is you had 1.25, you had 2, you had 3.25, but you didn't have this 5 here. Instead, you had a 1 in the beginning. So that's the only thing that's really changing. Again, you're going to notice that everything is the same if you look at all your numbers. You had this in the last one. You had this in the left approximation. You had this one, but you did not have this one. So it's your endpoint that's going to change here. So you need the areas of all these, and you need to sum them. Kenny?
So with more triangles, that 5 would be smaller?
With more rectangles,
Yeah, sorry. Right.
the 0.5 becomes smaller. Not the 5.
Another 5 either? Oh, sorry, yeah.
5 is the height of the function at the end. It's the height either way. It doesn't change. Okay?
I think it's a triangle, isn't it?
So here, we have area total is going to be half of 1.25 is
Half of 0.75? Yeah, 0.7. No.
125, not 1.5, guys.
Oh,
2.5.
Come on, these are ones you gotta know. 6125? No? Eighths? This is really what?
Yeah.
1 1/4?
Yeah, so
Right?
it's-
1 1/4? Half of 1.2 is 0.6.
0.5.
Half of 0.5 is 2.5, so 0.625.
Oh, wow.
That's the first one. The second one, half of 2 is just 1. The third one, half of 3.25.
0.1.
Same number again.
One.
Okay. Notice the same numbers there because the 0.25 and half of 5 is just 2.5. So what I want you to notice is this. When you sum these together, and again, I didn't factor out the width in this case. It doesn't matter. Sometimes it helps you. When there's only 4 rectangles, it really doesn't make too much of a difference. If you have like 20 rectangles, then make sure you factor out that and make it easier on yourself. When you sum these up, what do you get?
5.75.
And the last one, what do we get, Kerry?
3.75.
Notice, one is over, one is under. If we do the midpoint, what do you think we might get?
Get the mid, average of both.
The average of them both, we'll probably get 4.75. Again, 3.75, 5.75, 4.75.
Just coincidence that they're different. It's exactly like the interval.
It is a coincidence, yes. Again, notice that interval length was 2 from 0 to 2, and the difference between this and the left approximation is also 2.
That's a
5.75, 3.75. Carry coincidence. Again, it's a coincidence because it does not apply to all functions. With something like a quadratic, it might not be a coincidence. It might happen over and over again. You might see this. But the minute it changes from like a cubic or to a cubic, it's no longer going to consistently happen that way. Now, the next one is the toughest one. Okay, because we got to do the midpoint approximation.
How do you know when to? Oh, yeah, you know when.
All right, so here's the hard part here. If I break this into 4 rectangles, I got the same starting points again. Okay, same thing, 4 of them. But now what do I have to do? I started on the left earlier, then I started on the right. Where do I have to start?
That's in the middle.
In the middle of each
Also,
rectangle.
needs
Yeah,
to
break it again.
Okay, so look, the width is still 0.5. Start in the middle of the width and go up and put a dot here. Now put a flat line and just come down.
How's that hard?
Okay? It's hard because the math, you're going to have to use 0.25. Your decimal is going to get really messy. It's the only reason it gets more difficult, is because of decimals. Here, the width is 0.5. Start at the middle, go up, put a dot, put a horizontal line, go straight down. And you'll notice your overage and your underage are always going to try and cancel each other out here. Next one, start at the middle, go straight up. So I go straight up until that point. I get to the point. I go over in both directions, and I come down. Finally, go up again. Find the midpoint, go over, come down, come down. There's my 4 rectangles for this one. We're going to practice this, so don't worry if it's a little tricky right now. But again, start at the middle, go up, hit the function, make a line. Go up, hit the function, make a line. Make a line, make a line. And again, you're going to notice here that anything that's over has an under counterpart. Okay, whenever you do a midpoint, the over and the under are going to try and cancel. So, the issue with this is, yes, the widths are still 0.5. But now I need to know what the height of the function is at these points that I'm about to indicate. 1, 2, 3, 4.
We have to do this one.
Okay, so we're going to have to use the decimals. So for this one, what x value is this right here? 0.25. What's this one?
0.75. 1.25. Repeat.
Everybody has.
Okay, again, when I plug these in to find the height of the function, I'm going to have to take, to find this height, I'm going to have to run 0.25 through the function to get what the height is there. To get the height of this rectangle, I'm going to have to now run 0.75 through it. To get the height of this rectangle, I have to run 1.25 through the function. To get the height of this rectangle, I have to run 1.75 through the function. Okay, it just becomes a little bit messy. So the area of the first rectangle is going to be the width, which is 0.5, times whatever the function is at 0.25. The width of the second, or the area of the second, still going to be 0.5 as my width. Now my height is f of 0.75. The height at 0.75. The third one, the fourth one. Okay? Again, all you're doing here is you're plugging in whatever the midpoint value was for the x into the function. And remember, this is your width column really, and this is like your height column. Okay? That is your width column, and the other one is like your height column. Notice your width doesn't change because we have the same intervals for each one. Going through this process, what do we end up getting? 4.625 it turns out to be.
For the total?
The total area, if you did this, if you find the area of each of these, I can give you the values if you want to know. This one right here turns out to be 1.0625. Okay, I'm just going to dictate. I'm not going to write it, so if you want to write this, you can. Again, this one here turns out to be 1.0625. This turns out to be 1.5625. This turns out to be 2.5625. And the last one will turn out to be 4.0625. Okay? Knowing those numbers and multiplying through, you end up getting an area of 4.625. Now, sure, that's not exactly halfway between our left and right approximation, right? But it is between them, and that's the whole idea. The left approximation was under, it was 3.75. The right approximation was over, it was 5.75. This is our best estimate as of right now. Ken?
Yeah. No, because they, yeah, come on.
Just so you know, the exact area under this curve turns out to be 4.6 repeating. That's the exact area. So you can see how pretty close this is, isn't it? Compared to the last two. The last one was 5.75. The one before that was 3.75. So those were way off. This one is relatively close. This is the exact area. This is really the integral of f of x from a to b. That's what we did today. That's the exact integral.
Why do you write it from like the bottom A to top B?
Lower to upper, always. Just the way it works. And you'll see later when we start plugging them in, these are gonna have an effect on the problem when we do it algebraically. Okay?
So, hold on.
Good?
So we wouldn't put the 4.625 in that.
This is our approximation using MRAM, midpoint rectangular approximation method. This is the exact answer. I'm trying to show you that our midpoint was the closest out of all three. Okay, to summarize, let me summarize for you. Let me summarize. With four rectangles, using LRAM, we got 3.75. Using RRAM, why do I keep making M's with three squiggles? 5.75. For MRAM, we got 4.625. And the exact was 4.6 repeating. That was with four rectangles. Now, again, with four rectangles. In case you're wondering, let's say we do 8 rectangles. And there are programs that can do this in like 2 seconds for you for this kind of stuff. If we're doing 8 rectangles, you end up getting, for a right approximation, 5.1875. For the left approximation, you get 4.1875. For the middle approximation, you get 4.656. And again, the exact is still 4.6 repeating. That's never going to change. What do you notice happens as the number of intervals goes up?
The left and right change, pretty much.
The left and right changed. They got closer, didn't they, to the answer? And the middle actually did too. If you look at it closely, guys. Look at the middle. 4.62, 4.66, almost. It's almost exact, really. It's off only by a little bit here. So as the number of rectangles goes up, the approximation gets better and better. And that's what we stated earlier. Kenny?
Question for for the middle approximation. Is it always going to be like so accurate with so little, or it's just because it's a parabola?
It's just because it was a parabola.
Okay, yeah.
If you have a function that's like exponential growth with a sine wave in it also. You have something that looks like this, or might go like asymptotically, like bigger and smaller. It's going to be very different. The middle is always the best estimate still, though. The middle is the one that we're going to use.
Yeah, I'm
here.
wondering because this one is really close even with just 4.
Yeah, and that's, again, because this is a parabola, if you're doing this by hand on the test, it's going to be a very simple problem like this, okay? It's going to be a very simple problem. Now, in case you're wondering, just so you can see what it looks like, let me just bring this up real quick. Just in case you're wondering for looks of what this looks like. Okay, here's 8 rectangles. So take a look. When you do the right-hand approximation, this is the one I just gave you the data for 8. You notice all these overages, and you notice when you want the rectangle height, you start on the right side of the rectangle, you go up to the function and then make a line. Go up to the function, make a line. Go up to the function, make a line. So every time you're doing this, every single time you're doing this, remember, start on the right. So start on the right side here, go up, then go over. You start on the right side, you go up and over. Start on the right side, go up and over. Remember, every single time you're going up and over. When you start on the left side, you literally start on the left side, up and over this way. Up and over, up and over, up and over. So it's always where you start that matters. With the midpoint, though, notice where are they starting? At the middle. So they went up with the dashed line and then made a flat line. Up and over. Up, flat line. Up, then a flat line. Up, then a flat line. It's the same every time, but different techniques have different answers. The only difference you're going to have
Maybe under the,
is that... Go.
under the exact number.
Exact area.
Yeah.
This is over. You see all these little extra spots here, Jasmine? This answer is above the exact answer. Remember, the exact answer for this problem was 4.6 repeating. Look at this estimate. Isn't it over? Because of all these overages. On the right side, because of all the underages, or that's not even a word, but all these deficits here, these missing pieces, this value turns out to be lower than the exact. But when we take a look at the midway, we see that a lot of these overages are accounted for by the missing pieces. So even though we had all these overages here, and they weren't accounted for, but the underages weren't accounted for, over here, they do kind of cancel out. So this little extra piece right here is pretty much trying to cancel off that missing piece there. And this is what Christian said today. When he had all those extra little pieces, he made another rectangle on the side, just saying that these were all the missing pieces. And you can do that, okay? But the idea is this. The idea is that where are you starting? So here, when you want to find the height of this function, you plug in, when you want to find the height of this rectangle, you do f of 0.25. But for this one, you're doing f of 0 to find its height. For this one, you're doing f of 0.125, which is the midpoint here. So it's the height that screws everybody up. It's the height of the function that is changing. Let's do a bunch of examples now. Meaning a good amount. Let's start with an example. If we have, and we're going to do all 3 methods. Again, we're going to do all 3 methods. What we're going to do here, though, is we're going to go from 0 to 4, and we're going to have 5 rectangles this time. It's going to be a little bit more confusing. So let's say f of x is equal to x cubed minus 5x squared plus 6x plus 5. That's our function. We're going from 0 to 4. And we're going to say that n is equal to 5. So we're going to have 5 rectangles.
So they always give you the shape of the function if it was not calculated.
You don't need a shape. You can do it all with tables, and that's what we're going to eventually get to. I'm going to give you the shape right now to give you a sketch, but there's easy ways to do it with just tables alone. You never actually need the shape. That's the cool
All
part.
you need is like the width and the height.
Yes, you need the width and the height for every rectangle. And if you can somehow visualize that in your head, you don't have to worry about it anymore. Now, the general shape, though, because I'm going to give it to you for now until we get a little further. What's the y-intercept? 5. Okay, again, it's 5. So we're going to only go to 5. At the far right, the height of the function is going to max at 14. Okay, so I'm going to go 15, 10, and 5. On my y-axis, on the x-axis, I'm going to go from 1 to 4. Okay? So I start with that. Again, the only reason I knew only go up to 15 is because I have the sketch in front of me, and I know that the highest point is around up to 14. Okay? It doesn't matter though. If you can figure this out yourself, it's fine as well.
I thought we only have 5 squares.
What?
You said we only have 5 rectangles. We only have 4.
I'm only showing tick marks right now. In a minute I'm going to change those, but I'm just showing tick marks for now. Okay? And it's 5, but no, there's only 4 here. He made a good point. Look, there's only 4 rectangles here. Eventually we're going to have to change these numbers, but I'm showing you just what a normal scale looks like. Okay? Again, in a minute we're going to change what these interval lengths are. So this is the general shape. Let's draw it. We have, it goes up until 1, it dips down back at 2, through 3, and up to 4. Okay? You're just sketching right now. That's all you're doing, people. You're just sketching. I want you to do this because I want to see that you don't need to do it in the end. Okay? I want you to go through this process and see how tedious it is with this graph. And then at the end we'll make a conclusion and realize you don't really need the graph. You can use tables of values always. Houston.
I was going to ask if that was going on. We had to tell.
If it was what?
Doesn't matter. The curve.
It's increasing until it hits its local max, then it's decreasing until it's local min, then it starts to increase again.
Your calculator doesn't bore you.
Now,
If you have your calculator.
here's the tricky part for this problem. You have 5 intervals, and the length of the interval is 4. What is each width going to be?
4
what?
0.8.
0.8. Where'd that come from?
4 divided by
4 divided by 5. 0.8. Again, remember, the width is equal to b minus a over n every time. Now, if you're looking at your calc textbook, they're going to call the width delta x, just so you know, which makes sense. Delta x is my width. So if you want to start calling that delta x so that you're not confused, that's fine. Okay, but write the word width next to it so you remember. B minus a, well, delta x is simply going to be 4 minus 0 over 5, which is 0.8. So every single rectangle in this problem will have a width of 0.8. So that means that, take a look. This is going to be the end of the first rectangle right here at 0.8. Then what's another 0.8 going to be? 1.6, which is like here. Then you're going to have the next one, 2.4. The next one, 3.2. And then the last one, 4.0. So believe it or not, the rectangles are going to start and begin at all these dots. So all these tick marks that were on here originally, they don't really do anything anymore. Again, I know it's on your graph, and that's fine. I understand that. But the important parts now are these dots. So let's indicate what these dots represent. So again, this dot is at 0.8, 1.6, 2.4, 3.2, 4.0, and that one was at 0. Noticing now, we're going to have 5 rectangles.
Okay. When you have to graph it on a table. If you're at the graph on a table, you have to know that, and you have to know the half.
Well, once you get to the table stuff, you're just going to start doing f of 0.8, f of 1.6,
No,
f of this.
But that's if you're doing the f is if you're doing the right though. But if you're doing the center, the middle.
Just wait, just wait. The middle, sure, the middle, yeah, you're going to use 0.4, you're going to use 1.2, you're going to find all those averages. But for the left and right, you're going to notice that there's a very simple way to do it. For the middle, yes, you're right. The middle does get a little bit tricky. Now,
should we start from 0 and you go to?
should we start from what?
I was saying for the left, you start from 0.
For the left, you start from 0, and you end when you get to the 3.2 with your rectangle there. From the right, you start at 4, and you end when you get to here. From the midpoint, you literally go from each midpoint and make your rectangles. Okay? So, let's go ahead and do this. I'm going to show left first.
Do we need to do all 3 methods, or are you just showing us?
I'm showing you that,
All right.
but the test can ask you for any of the 3. It might say, find an LRAM of the following function where n equals 4 and the interval is from 0 to 7.
So
Well, that's your interval, that's your that, and LRAM means left approximation. So you need to know how to do them all. And you know what? If it's a part 2, it might say, a part 2 could say this, guys. A very simple part 2. And I don't mean simple as in easy, as in simple as in basic. Find LRAM, find RRAM, find MRAM, that's A, B, and C, and then part D will say, find the exact integral. And then it'll say, explain the differences here. Explain them. Left RAM is an underestimate. RAM is the overestimate. MRAM is the middle point between them, and that is the closest to the exact value. So what we just did with that last problem could be a part 2 problem. It's very rare, though, that they have Riemann sums on part 2s. Okay? They're usually part 1s. They're usually part 1s. If they're part 1s calculator, we're going to have a program that does it for us, where you could select left, right, or middle. It'll ask how many rectangles, what is your interval from 0 to what, or from what to what, and it'll give you the answer. Okay? There is a program to do that. If it's by hand, we need to know how to do it by hand. So for this one, can somebody come up and draw left RAM? Left RAM.
I can do it.
I say, I nominate that. That's stupid.
I nominate one of the 3 of you that just raise your hand. So decide.
Yeah.
There's 3 of them we're going to do, so you don't have to do it right now. You want to
Which one is
start?
this one? Which one?
LRM, left approximation.
Left. How do you use this?
I'll give it back to you. I want you to use a marker, though, please.
Don't call me boy.
Okay, he's good so far.
I did watch the top there.
So we'll just go.
Good. Use your technique and keep going until you get to the end of the interval.
So get here. So
Until you get to here, keep going, keep going,
Oh, so
keep
just
going.
keep going.
No, keep going with the flat line. Now go straight down. Okay, stop. Start here, go up to the function, go over until you get to 2.4, and then go straight down. Start at 2.4, go up to the function, go over until you get to the next interval. Then start at this point, go up to the function, and then go over, and then go down again. And that's exactly right. Notice this time, what kind of a function do we have, guys? It's not quadratic anymore. What is it? Cubic. And take a look. Underestimate, overestimate, overestimate, underestimate, underestimate. So when we don't have something like a parabola, or something where it's constantly increasing, this function is increasing, then it's decreasing, then it's increasing again. The fact that its first derivative changes signs and it goes from increasing to decreasing indicates to us that we're going to have not only under, but over spots also. Okay, again, this is LRAM right now. That's the left-hand approximation. Because he started on the left, went up, over. Started on the left, went up, over. Start on the left, go up, over. Start on the left, go up, over. Start on the left, go up, over. And you're done. These are your 5 points to start at. Notice, the 4.0 does not really get used here. But when we do the right approximation, we're going to start on the right. And then the 0 won't be used. And then when we do the midpoint, we're going to start all the midpoints again. So, we have to go ahead and figure out the areas of these. What is every width going to be, everybody? 0.8. So, if I want the total area, I'm going to normally find the sum of all my widths times heights, right? But since the width is constant, I can bring the constant out in front. So every time, factor out the width, please. And then just write whatever the heights are as sums. Okay, again, because the width is constant. The width is always going to be 0.8. So the width can be factored out of the summation sign. Put the width out in front, like that, and leave the inside as the sum of all the heights now. Okay, because remember, it's the sum of the areas. Area is really width times height.
If on like a part 2, they're asking you for like, you know, to do all 3 approximations, and let's say they say it's always going to be like n will always be 5, and you do the left approximation, you do the right approximation. Is there a way to algebraically like
Find the mid approximation based on the other two?
based on those two? No.
There's no formula that gives you the exact value. No.
Yeah. That was just wondering since you had the 2, if you wouldn't need to do like.
Yeah, I got you there. No, Kenny. Here's the reason why.
What?
The function changes in a cubic manner. If the function changed in a linear manner, it would work. That exactly would work. If it was something like y equals 5x, and it was a line like that, and you did a right and a left and then a middle, it would be the exact average. Because it's that. Just because it's linear. Because this is cubic, its rate of change is different depending on where you are. That's a little bit more thought than what we're going to be on here, but keep that in mind. So when you factor out the width, yes, it's 0.8. I need to figure out, though, what each of these heights are. Again, this is 0.8 times the height, 0.8 times the height, 0.8 times the height. So, if I want to find the height of the first rectangle, the height, what do I plug in? Okay, good. That's fine, Karen, but slow down, please. I know you're there. What am I plugging in? 0. Thank you. Again, the first height is going to be f of 0 because I'm trying to figure out the height of this rectangle, which is dictated by the 0 here. The height of this rectangle, it's dictated by the function right here. That's where it meets the function. So there I'm doing f of 0.8. Next, the third rectangle. To find the height of the third rectangle, what would it be?
1.6.
Very good. F of 1.6. After the 1.6, that gives, again, the 1.6 gives me the height of this rectangle, the third one. Then I want to figure out the height of this rectangle. It is based on what? 2.4. Because again, at 2.4, that's where that height comes from. And then finally, the last one?
3.2.
3.2. Now, why don't I care about the 4 again? Good. We're looking at all the left side approximations, okay? So once you figure out all these values, you got to run them through the table. So please don't do this by hand, okay? If it's a problem on the test where it's no calculator and you have to do this by hand, it will not be a function like this. You're not going to have, this x cubed minus 5x squared plus 6x plus 5, because that would be a bit of an annoyance, right?
Sit there.
If it's a non-calculator part, it's going to be a problem like the first one, where it was x squared plus 1, because those fractions are very simple. Karen, I see you plugging away. Did you get all these values already for me?
Yeah, I got 80.
You got them all, or you got one of them?
I got all of them.
And they total up to be what?
Oh,
Or you want to give me each?
Let's care.
No.
The entire area.
What'd you say?
I got 81.5.
He actually did the answers.
Give me those times.
For the entire area.
Oh, that's 28.
Okay.
Yeah,
Usually,
So just give me each individual one though first.
oh,
that's right.
7.116.
I'm approximating.
5.89. 4.424. 5.76.
Okay. So again, the height of the function changes based on my location. Obviously, when we're at x equals 0, there's that height. When we're at x equals 0.8, there's that height. The sum of these heights turns out to be what value? 28 point. So the actual area we get from this approximation, oops, sorry, turns out to be what?
You only do 22. You only do it again.
No, I trust you. It sounds right. Let me do it. 12.1, 17.1, 18, 22.4, 27.4, 28.2. Okay, now, before you leave, sit down, because we're not done. Give me another minute. The area here, again, the area here is an estimation. We don't know right now if this is an under or an overage, actually. We don't know. Because remember, look at the shape, guys. Part of it was over, part of it was under. I would guess that it's an underestimation because of all these missing pieces that are much bigger than the pieces that are over. Do you see what I'm saying? Again, as an estimation. Now, what we still need to do is RRAM and MRAM. Then what we can do is figure out the exact value and compare and see what happens. What I want you guys to do tonight is this. Again, you're reading those pages, 263 to 269. I put that on Edline and Facebook already. You see it there. 263 to 269. What I want you to do tonight is simply this. Try these 4 problems estimating with rectangles. And I'm not going to tell you to use L, R, or MRAM. Use anything you would like. But just practice finding the area under the curve. And please look at the domain that's given. So from 0 to 5, you're only going from 0 to 5. So you're finding the area underneath that little hill there. You're not finding all this other stuff. Now, the first 2 are graphed. The next 2 are not graphed. Okay, so draw yourself a sketch using your calculator for these 2, and then approximate. This is a very, very generic approximation. You're not using LRAM yet. We need to continue to do a little bit more before you work on your homework for that. Okay?
We couldn't do it if we wanted to?
If you want to, please go ahead and take a look. I have 2 more worksheets for the next 2 days for LRAM and MRAM. But if you really want to practice those problems, there are more problems in the section in the book you're reading.
So
if you want to practice RRAM and LRAM tonight, please go ahead and look in your textbook at the practice.
So this was so which one is this? Is everyone-
Anything. You can do just like we did in today's lab. I just want you to approximate the area any way you would like. use trapezoids, triangles, rectangles, whatever you would like. Eventually, we're going to learn about something called trapezoidal method, okay, where we actually purposely use trapezoids. Thursday, remember guys, Thursday.